Okay, so welcome back. We have arrived to the last session of this INSPYRE 2016, and I wanted to conclude these days of various type of activities, including lectures, including some experiments, including hopefully a bit of fun, with a presentation of what I believe are some kind of 7 big questions. Of course, the list is not limited to these 7. It could be much longer. But I choose to show you some of the big questions which I believe are still in front of us and needs to be explained in the near future. And hopefully some of you might contribute to disentangle and to solve some of these remaining open questions. We have seen this morning that one of these questions, the gravitational waves, has been solved, and this opens new window towards a search in the universe. But however, so what we have seen these days is that the universe, starting with the Earth, then going on towards a bigger view, we have a rather good understanding of our galaxy, even if not as complete as we wished, because as I'll show you, there are some open questions related to dark sector of our universe. We know, however, that our galaxy is composed of 100 billions of stars. We know stars, but maybe not as good as we hope to know them, or as we might hope to know them in the future. We have an overview of our universe. We have seen, I was presenting you the idea that this might be only a part of a much larger universe under the parallel universes, but this is, however, what we have observed up to now. This is the observed universe, taking into account, however, only the electromagnetic radiation. If we think about the possibility in the future to get more knowledge, a broader knowledge with the gravitational wave, this image might change or might be completed, and we might discover extremely interesting phenomena, which for the moment we might not even guess. And we know as well that the universe had a beginning, at least the universe as we know it, in something like 13.7 billion years ago, in this unique event which is called the Big Bang, out of which the universe evolved, starting with something which we invented, theoreticians invented, the inflation process, in order to explain the uniformity of the universe as we see it today. So we still do not know whether the inflation process has a root in reality. There is a field which might have triggered that inflation. We have seen that the universe evolved. We might reach with our experiments, for example, the Large Hadron Collider, a state of matter which is quark-gluon plasma, which might be similar to what has been in the beginning. Then we have some light after 3,000 years ago. We have kind of this cosmic radiation microwave background, which gives a lot of useful information from that date. We know as well, so that's for what concerns the big universe. For what concerns the particle world, we know that the normal matter world is done out of particles contained in the so-called the standard model of the particle physics, where there are many quarks, well, not so many, 6 types of quarks, then electrons, neutrinos, and some other muon. Those who have done the experiments with cosmic ray have had met muon from a closer view. The Higgs boson has been recently discovered at CERN, so we are quite happy. We have a kind of nice view about the world of particles, but we also know that there are many, many things which the standard model does not explain, among which the gravity, because gravity is unfortunately not yet discovered as a quantum version, so we don't have a quantum version of the gravity, which is one of the biggest problems today. So after having told you what we know from the universe to the particles in a very quick overview, the 7 problems I want to bring into your attention very briefly are the following ones. So that's a list, and I will start briefly presenting each one by one. So the first one is referred to what happened to antimatter. This is a very kind of easy question to ask, but very difficult still to answer, in the sense that we have seen when we were discussing about the birth and evolution of our universe, that what we were expecting, and actually in the standard model, with respect to what I have shown you before, that's not the true story, and actually not the whole story, because a part of particles in the standard model, there are as well the antiparticles. So to each one of the particles in the standard model, it corresponds an antiparticle having opposite quantum properties, like charge or the spin or whatever. So the real question here is where this antimatter disappeared, if we consider that at least in the standard theory related to the Big Bang and universe evolution, in the beginning, they should have been born in equal number. So when the universe was born out of this Big Bang, unless our model is completely wrong, but, well, for the moment we don't have traces that this model could be wrong. So unless this model is wrong, we believe that in the beginning, when the universe was born, particles and antiparticles were born in equal quantity, in equal number. And in the very beginning, one microsecond after the Big Bang, most part of them annihilated. However, there is something which survived, and this is us, for example, or the universe as we see it. It's composed completely only of matter particles, and we know this because if it should be some island of antimatter in the universe, we would expect that when this island meets somehow at the interface with the matter, it should be a big energy release out of the annihilation between matter and antimatter in the borders between the two. Since we don't see this in the universe, we deduce that there is no place for antimatter, at least to our view of today. We have at least seen, this is, for example, an image of what an antihydrogen would be, and I show you this because antihydrogen, it's really studied, it's produced and studied in various experiments, most of them at CERN, but not only there. So you get here an antiproton produced of antiquarks with -1 charge, around which a positron, we have met the positron before, here the positron is staying around an antiproton and would create this antihydrogen atom. So this antihydrogen is studied together with many other antiparticles just to see and to check once more whether the laws of particles are equal or similar or different with the world of antiparticles. And here, actually, Pavel Moskal is a specialist in this. He is working on this, studying that there are laws which are different between particles and antiparticles. CP violation goes under the scientific name, so this is charge symmetry and parity combined violation, which is presently studied in the Chloe experiment right here in Frascati at Daphne, and you have seen Daphne. And it's as well studied, for example, at CERN, but there are experiments in Japan and in China which are studying the same things. So we have indeed discovered differences between the laws of matter and laws of antimatter, but these are not enough for the moment to explain the completely disappearance of antimatter. So in spite of the fact that we do have kind of hints for an answer, it's still a big question for the future, because what we have measured, it's not enough. But when I say it's not enough, it's not that it's missing 50%. We have uncovered 50% of the asymmetry and some. We unfortunately uncovered less than 1%. So what it's missing, it's a huge asymmetry, or it's something deeply rooted in our ways to see the universe. So this is a kind of a representation of the parity violation. So the mirror image of the particles, in this case, do not exactly do what the particles are doing. So we hope to have an understanding of why matter remained while antimatter kind of died away in the past, actually in the very first instant of our universe. And this is something which is a big open issue, in spite of the fact that we do have some hints of which the answers might be. We have to look into neutrino sector, and we might uncover some big part of missing asymmetry. So this is one thing we do as well in Frascati on the Daphne Collider, a part of many other places in the world. There are difficult experiments because the difference in the laws are by 1 per 1,000, so you need to be very precise to have detector systems which are able to have to work so properly. This is the Large Hadron Collider where similar measurements are done. This is an image inside the Large Hadron Collider, 100 meters underground, where there is this 28 kilometers. You have seen Monday, closer view about physics, which is done here. While this is the LHCb experiment, which is dedicated purposely to study differences between matter and antimatter, particles and antiparticles. So the second big question is, of course, related to the black holes. I'm saying of course because black holes were always very much interested for scientific community, but even for general public. Today, even more than yesterday, just because the gravitational waves were uncovered, and not only that they were discovered, but they were discovered from a connection, strong connection with the black holes, as you have seen in the very first talk this morning. Ok, vabbè, qui c'è un errore. Okay, so the mysteries of the black holes, it's somehow related with many figures. You have seen Stephen Hawking before, which is actually, I don't know if you read, it was a paper he had given 1 week ago, a BBC lecture, where he was even saying that if we would be able to create a black hole and somehow to hold it in orbit around our Earth, a black hole with a mass similar to a mountain, which would be a very small black hole, that black hole might give the energy out of the Hawking radiation, which would be our energy source for the next 100,000 years. Of course, then we have the problem how to create. If we want to create such a big hole, we might need bigger energy than what is released afterwards. But okay, fantasy, it's always nice. We have seen that black holes are not seen directly because the light cannot escape out of them. What we see is objects falling inside, and this was up to 1 week ago the only way to see them. Now we have a new tool, and this new tool are gravitational waves, which might give us something new because these signals are coming directly from the black hole. And it was a question before, what happened if you sum the masses of the two black holes, at least those which collided together, you didn't get the mass of the final merged black hole, because as Viviana explained, what has happened is that the missing mass was transformed in energy of the gravitational waves. So the gravitational waves bring information directly somehow from the black holes. It's not some radiation coming from an object which falls down in the black hole. But we still need to work on that. It's still a new tool and a new instrument. We have seen that the relativity is our instrument to first to understand the origin of the black hole, but it's in the same time the limit of understanding the black hole, because exactly the relativity is predicting the puzzling feature of having a singularity, actually an infinity, when the density of matter becomes such high that this curvature of space-time goes to infinity. So the mystery and the big question here comes directly from the equation of Einstein of general relativity, which relates space and time with the additional term which will come over again. For the moment I don't comment it. So space and time structure with the matter structure. So the question whether space and time can exist without matter, what you asked before, I think it's still an open question, because space and time are strictly related with the, actually here is not only matter, it's matter and energy. So it's the content of matter and energy. And at some point you have seen this, there are spectacular confirmations, starting with the first one, which was the Eddington discovery of the deviation of the starlight beyond the sun by comparing what happened during night with what happened when the sun was there but covered by the moon. So we could see that somehow was a sudden change between the position of the stars, which could only be explained by this change in the geometry of the space and time. These are the two gentlemen nicely chatting together many years. So Eddington with Einstein many years after this brilliant discovery, rather adventurous one, because 1919 they didn't do it from England. They have done this measurement by putting everything on a boat and starting a competition. They were not the only ones. There were 4 teams starting and aiming to do the same measurement, first arrival, first to be remembered in the history. So if Lord Eddington would have been the second to do the measurement, he wouldn't be so famous today. So as I told you, there are some conditions in which this curvature goes to infinity. So it's a singularity. And this singularity in physics, it's something which we don't like, which we don't consider as real. So something which is missing from the theory, and this is probably the quantum version of gravity, might smooth this infinity and bring it back to what it's allowed, at least in physics. So while the sun and even neutron stars do produce deviations or curvature which are easy to cope with and which are perfectly in line with what Einstein predicted, when we deal with black holes, this is something very mysterious and an open question. So the black holes, for the moment, what we can hope to have, it's, for example, some smaller black holes for which this quantum effect, which is Hawking radiation, which in 10 seconds explanation. Hawking radiation, it's that type of particles which are coming out of the vacuum fluctuations allowed by the quantum physics, which are quantum fluctuations, so antiparticles produced not far from the horizon, but very near the horizon of the black hole. And one of these falls into the black hole, while the other one, instead of remaining virtual as a fluctuation of the vacuum, becomes real. When the particle becomes real, this happens by sucking energy from the black hole. So in the end, if you have a lot of radiation, the black hole evaporates. So emitting these particles, which are real particles which we can measure, the black hole in the end disappear. Why we didn't see it for the moment? Because this radiation goes with the inverse of the mass of the black hole. So the black holes, which are enormous, basically all those we know, the radiation is overwhelmed by what the black hole eats. Not last, the cosmic microwave background radiation. So a huge black hole will never evaporate, at least not in the next billions and billions of years. So that's our hope, to get a small black hole for which the radiation emitted, it's much, much stronger. Remember, it goes inverse proportional to the mass. So if the black hole is very small, it will evaporate immediately. So this might help us to understand, for example, and to answer to the very often asked question, what happens if one of you would drop inside a black hole? What will happen with him? And this might hopefully receive an answer in a near future, which is sought for almost 100 years, because Einstein was aware of this problem. Of course, one cannot not ask the question about the dark matter and dark energy. So we know by now that the universe has a dark side which not only it's present, but it's overwhelming. So when we think about the budget of energy and matter inside the universe, we see that actually the most part of it is dark. How these were discovered? So the dark mass was discovered rather easily, and it's even rather easy to be explained. Many years ago, tens of years ago, when the galaxy was still studied in details, one of the measurements which was done was the speed of the peripheral stars in our galaxy. And the speed of this galaxy, so the velocity, the velocity to which they moved, is proportional to what? To gravity. So it's proportional to the gravitational attraction, gravitational pull by the mass of the galaxy. Similar how the velocity of the Earth around the Sun depends, of course, on the distance from the Sun, but on the mass of the Sun as well. In a similar way, the velocity of the stars in the periphery of the galaxy should depend by the mass of the entire galaxy. So people were able to measure this velocity and to compare it with what was expected from what we know is inside the galaxy. And it was a huge unmatching between the two quantities. The velocity was much, much bigger than what was expected to be. And this could have been due to two reasons. One, that gravity at this scale is wrong. So Newton, Einstein does not work, so we have another law. The second version was that there is some mass inside our galaxy that we don't know. And this was called the dark matter inside the galaxy. Why, in the end, we believed more in this second version than in a modification of Newton's and Einstein's law? Because this is not the only effect which has been seen, which tells us that there is dark matter in the universe. There is gravitational lensing too. So there are many additional proofs about the fact that dark matter is indeed there. And the answer cannot be, you want to ask something? Oh, sorry, I saw your hand. So dark matter came originally from measuring something which looked trivial, but was not, because give us an overview of what is in the universe, what is in galaxies. And in our galaxy, apparently, there is 10 times more dark matter than normal matter. This is a huge problem, embarrassing huge problem. A part of this, when we look at the entire universe, by the end of last century, when we could measure the redshift of the stars, of the faraway supernova, and we could check better the expansion, so the Hubble law, we discovered, as a huge surprise, the fact that the universe expansion was kind of accelerating. So by the fact that the velocity of this faraway supernova did not match a linear Hubble law, linear means that the velocity is proportional to the distance from us, but it's not linear, but it's having a term which introduces an acceleration. This was, again, a big surprise, not so old ago. Was 97, 98. For you, it's old because probably most part of you were not yet born. But however, it's for the history of physics, it's recent. So we gave the name of dark energy to the source of that accelerated expansion, because we know it cannot be gravity which would pull things back together. So that's, again, something which is tantalizing approach to the modern physics, and introduce a huge, huge problem to answer. So we know for the moment that what is the budget of matter and energy of our universe, it's something like that. So we know an embarrassing small matter, we can name it, stars, dust, planets, ourselves. We are only a mere 4%, unless we got it wrong. So the rest of it is dark matter, a huge quantity of dark matter, which we search for, and moreover, the mysterious dark energy, which we struggle, not only to understand, but to invent methods to measure it. I don't hear you. Dark matter, I'll come. So these are the problems, dark matter and dark energy. And while for the dark matter, we have some hints that what could it be, and here is one of our hints. If we assume that our standard model particle physics, it's having, let's say, twins and brothers, each particle in the standard model has a twin particle with higher mass in the so-called supersymmetric model, where to each particle it's associated a twin, so a supersymmetric particle with opposite spin. I have seen that Matteo spoke about this Monday, so he had given to you already some elements about the supersymmetry. So a good candidate of symmetry might be the supersymmetric model. But now, well, we didn't find any trace of supersymmetric model. Somebody asked me, and I want to stress this fact, that the fact if supersymmetric model would be true, we might expect in the dark matter sector a structure as rich as the one in our normal matter world. We might expect atoms and molecules of dark matter. Why not? So kind of a universe which lives together with us in the same way here out of dark matter. But again, we have no trace for the moment of the existence of this supersymmetric particle, so they might be something else. And this is a kind of a view why we didn't discover yet this supersymmetric particle, if any, if they exist. Probably because they are too heavy. If they wouldn't be so heavy, we would have discovered them for the moment. So either they are really very heavy, and then they might be discovered at LHC, or they might not, or supersymmetric model, it's simply not true. Then we have to go and dig back into the origin of potential dark matter and dark energy. So that's an open question. It's an important, fundamental open question, which experimentally might receive confirmations not only from LHC or accelerator-related experiments, but as well from the experiments in the underground laboratories, because here what we search for in the cosmic silence is some small signals, very weak signals, coming from the interaction of dark particles with our detectors. And here for the dark energy instead, while for the dark matter we might believe that there is the supersymmetry involved, at least for one of the candidates, for dark energy our way to explain it, at least in the general relativity, is by putting back in place what Einstein introduced as a cosmological constant. He put it there to keep the universe constant and stable, and then he threw it away when the cosmic expansion has been discovered. Now we put it back this time to explain another unknown feature, namely dark energy. Actually, I used the wrong word because this doesn't explain anything. This only keeps somehow the trace of it and actually hides our ignorance. So we don't know what is dark energy. We might have some hints that it's related with the vacuum fluctuation. We might have some hints that it's related with a field which is analogous to Higgs or something similar. But the true fact is that we don't know. So this is something which is probably the strongest challenge in today's physics. Not only to have an idea of what it is, but even more important, an idea of how to measure it. We have seen these days many detectors, many experiments, all of them aiming to measure something. Usually that something is difficult to measure, time resolution, space resolution, but we know what we look for. In this case, we even don't know what we look for. So it's very challenging. This is a sector which is, in the future, might bring us a lot of satisfaction, because discovering dark energy might teach us how to use dark energy, if any. And this might be extremely important for the future. Another item which I put here because it's the item on which I work, and because I believe that in spite of the fact that neutron stars are there, we have seen them, we know them, but we still don't know how they are really built. So we know, for the example, that in the universe, at least in the first instance, this standard model that I show you again and again contains, for example, 6 quarks. However, all the matter we know, all the matter is done from protons and neutrons when we speak about the quark sector. Protons and neutrons are only containing quarks from the first so-called family, up and down. And our body, all the matter in the universe, it's composed only out of the first family quarks. One might question whether the other families, like the second and maybe the third, but let's go for the second, might play a role not in the origin of the Big Bang, then we might easily imagine everything played a role. But today, is today any place for strangeness in the universe, for the strange quark? Why the strange quark? Because the strange quark is the less heavy among the remaining ones. So the place where we might imagine there is some strangeness or some strange quarks are the neutron stars, because the conditions inside of density, of matter, are so peculiar that if any strangeness is produced, we might believe that it is there. I might have spoken about the black holes, but black holes are so exotic that it's impossible and it's even wrong to imagine strangeness in the black holes. I want to imagine them in an object we know, in the neutron star. So the neutron star, seeing that it's weighting, one glass of this matter might contain 100 billion tones. So it's so condensed, the matter there, that if we would have, instead of an ice cream of neutron star, its weight would be this, 100 billion tones. The diameter of a neutron star, it's something like in the order of 10 kilometers, where the mass of the something bigger than sun, it's concentrated. So we can believe that in the heart of this type of stars, a part of neutrons, which we know that are there, might be placed for more exotic objects, for more exotic particles like lambdas, kaons, or whatsoever, which contains the strange quark. And that's what we are doing. Of course, we don't produce neutron stars, otherwise we would be sucked inside a neutron star. But we produce strange particles, and we go to study how they interact with the rest of the nuclear matter. This is Daphne. You have seen Daphne inside. And the experiment which we do that, it's called Siddhartha. And what we do is we create nuclei in which we replace the electrons with this kaon particle, which contains a strange quark. The kaon is much heavier than the electron, 1,000 times heavier, kicks it out immediately, goes and replaces it in an orbit around nucleus. This orbit for the kaon, it's a heavily excited orbit, and then the kaon wants to de-excite to its fundamental orbit. The kaon being so heavier and coming so close to the nuclei, this is a very, very small atom. It's much smaller than a usual atom. Much. It's a very teeny, very small atom, but that's not important. Important is that when it de-excites, it emits an X-ray, similar to the process Pavel explained us before, and this X-ray carries information about the way in which the kaon interacts with the nucleus, and this way it's not only out of electromagnetic, but it contains a part which is due to the interaction of strange quark in the kaons with the rest of the nuclear matter. And that's what we hope to obtain, and what we actually did obtain, and we continue to study with these detectors. That's silicon-driven detector, which measures these X-rays, which are produced out of the interaction of the kaons inside the targets, which form exotic atoms emitting X-rays, which we measure with our detectors. These are part of my colleagues mounting the setup inside Daphne a few years ago, and this is how it looked like, while this is part of the group when we have finished a first phase of data taking, and we hope to do other measurements again soon. This is the kind of things we see. I don't insist on it, just to show you that spectra are the main tool, histograms and spectra are the main tools of work, whatever kind of physics mostly you are doing. I then speak about, here it's missing a P, so about this, how many universes, parallel universes, and Schrödinger cat paradox, because this is related to the quantum mechanics. I put them together because I already told you about this, so I'm only making a very fresh, quick refreshment about these ideas, because we were discussing them by Tuesday. So we have seen that what we see, our observable universe, might be only a part of a much bigger, broader universe. So our visible universe might be completely embedded in a much bigger universe, which is not accessible to us because the speed of light, it's limited, so signals which are beyond the border of 13.7 billion years from us, since the Big Bang was by that time, did not have yet time to reach us. So we have here the question of the parallel universes. We have seen this, even with this puzzling question of if the universe is infinite and if the particles are infinite number, sooner or later you hit into the same type of universe as ours, and you might really get a same world as us, doing exactly what we are doing or doing different things, so really parallel world somewhere in the bigger universe. Parallel universe might not look like us or like ours because physics might be different, and this idea we again discussed Tuesday, the fact that it's motivated not only by imagination of science fiction writers, but it's motivated, at least in today's physics, by the string theory, which sees these particles, fundamental particles, as representing actually strings which are vibrating in 11 or 10 dimensions, and then out of this somebody has mentioned Calabi-Yau manifolds. So this string theory might predict existence of huge number of universes. And okay, we have seen this. Related to this, there is this extremely intriguing problem of the superposition in quantum mechanics, superposition which brought to the paradox of the Schrödinger cat, which sees a cat which is in the same time alive and dead. And this is, on one side, a big problem for the present quantum mechanics, because the standard quantum mechanics solves it by a principle. You put there kind of a rule. When you do a measurement, only one solution remains, even if quantum mechanics allows few solutions in parallel. And this is a problem which quantum mechanics deals with, is the so-called collapse of the wave function problem, which is the biggest problem in quantum mechanics. And one of the interpretation among many, it's this many-world interpretation, which connects it somehow to the parallel universe. But I have to confess that this is not only one of this interpretation, but it's also not only the most exotic one, but the less accepted, to be honest, by the scientific community, which looks maybe more into different sort. This is mostly philosophical motivated, ontologically based, while this is empirically based, looking for beyond Schrödinger equation. So there are many things in this sector, many worlds, many universes, quantum mechanics and quantum technologies. You have seen from the talk of morning of Mauro, which spoke about Mauro Paternostro, quantum technologies, that quantum features and quantum awareness, a part of being a resource for understanding better the world, it's in the same time a huge opportunity to eventually discover new technologies, going from quantum computer maybe to quantum tomography. And Pavel, it's now involved in some very nice and exotic future probable technology, which not only explore, as he was saying, the positronium, as he was showing in the last slide, he didn't have time, but he tries to explore quantum features to learn even something more. So quantum mechanics, it's a huge opportunity, a part of being a huge challenge for our mind. Last but not least, since this is a scientific question, are we alone in the universe? And one cannot avoid to ask this question, not only because it is extremely interesting one and because it's exciting one, of course it is, but because it's really a scientific question after all. So are we alone or are we not alone? So this undergoes under the name of Fermi paradox, because Enrico Fermi was the one who first, not that nobody before ever imagined that aliens might exist, but he was the first one who put the grounds for a scientific approach. Because once he was eating together with friends in Chicago, and at some point they were discussing about aliens and some jokes about that, and he suddenly stopped and actually asked, where they are, if they exist, why they are not here. And if you think a bit, this is indeed a kind of a challenging question, because if the universe would be full, if our galaxy would be filled with aliens, how could it be that they are not yet here? And there are many, many questions, many, many possible solutions to this question, and not only solutions, possible solutions, which are of course contradictory among them, otherwise we would know already the answer, but there is also a scientific approach. And the first scientific approach put forward is this so-called Drake's equation, which was put forward by 50 years ago or so, which is a multiplication of probabilistic factors, which gives us the number of aliens, civilizations, more advanced than ours, existing in our galaxy. So let's see which are these kind of factors. I show you, this is Drake himself, who has given many contributions in physics and especially in astrophysics. And this is a pictorial view of the equation we have seen below. So how many intelligent civilizations do exist in our galaxy? This depends on a series of known factors and a series of unknown factors. Among the first one, there are factors which we uncover more and more we study the universe. Star formation probability, more or less we know it. How many planets do exist? This again with the help of Kepler satellite that discover more than 1,000 planets. It's becoming more and more known. How many are suitable for life, at least in the form we know it? Again, this becomes more known as the time passes by. Then the second line, it's instead completely unknown. And it's a huge problem not only to look for aliens, but to understand our origin, the origin of life. So which is the probability once this is given, you have a planet, it's around the sun, everything, it's nice. How probable is that life appears on that planet? Not only that it appears like bacteria, but how probable that it evolves, it develops an intelligence, it develops a technology strong enough to be able to spread in the universe. We are not yet here. And last but not least, a very tragic, dramatic, and actual question. How long that civilization survives till either it kills itself due to wars or due to stupid things, or due to the fact that they didn't know how to deal with their Earth. They burned it, they polluted it, they suicided somehow. So the lifetime of an advanced civilization might be a killing factor as well. So all these are questions for which we don't know the answer, which tells in the end that basically when you calculate this number, you get whatever between 1 and 1 million. So the galaxy could host many, many civilizations, or might host none beyond us. This is the planets which we discovered up to now. New discoveries are done steadily, and this is again a very nice, challenging, and a beautiful type of experiments. You use sometimes relativity, some other times extremely precise measurements, because you don't directly see the planet. You see the fluctuation of the light from the star when the planet passes in front of it. And the fluctuation, of course, it's minimum. It's not that the planet covers the star. It only fluctuates by epsilon fraction of it. So what's the answer of this question? Of course, there are those who believe that aliens are here. They are naturally traveling. The UFOs are here, and okay, UFOs are here, and that's it. They are here. Unfortunately, or fortunately, or anyway, that's the situation. We do not have real scientific answer, so we cannot say that they are here. Many of these objects are natural explanations of natural phenomena, like globular sparks, like globular sparks, so they are, or some planets. So we cannot say that this is an answer which is provided with certainty. The other answer, I do now a very quick overview of possible answer, is that we are the aliens. We are the aliens. This is the panspermy hypothesis, which says that the life arrived on Earth either from the comets or from asteroids or somehow molecules, even bacteria, came on Earth from somewhere else. Of course, this doesn't answer to the question, where are the others, but might answer to a question, how much probable life is in the universe. That's the reason for which we do search life on Mars, we do search life on Churyumov-Gerasimenko with Rosetta, we do search life even in very primitive form somewhere else. The other hypothesis, and actually this is that one, that life was brought here, but by some other who really wanted to bring it here. So it's a kind of panspermy, but it's not instantaneous. It's a kind of directed by some other civilization. This is hard to believe because if somebody wants to send, let's say, a kind of a object with on-board bacteria, you need to make a very precise travel till you get there. And that's out of our, not only technology, one can say, who cares? They might be more technological than you. But the relativistic effect, the general relativity effect, and the fact that we don't really know dark energy and dark matter might screw it up completely if you really want to do a predictable calculation to do it for long range. Well, another answer is that extraterrestrial might not be able, as we are not, to travel very far away. So then we try to listen to them, to listen by signals. What signals? For the moment, the only one we could listen are the electromagnetic radiation. From now on, gravitational waves might be another source as well. So what our best ear towards the universe, among our best ears, is this Arecibo radio telescope from Puerto Rico, which is really huge, 300 meters in diameter, which is kind of trying to explore the full phase space of electromagnetic radiation. Of course, it's hard. Think about you have a radio and you don't know who is, you have only one radio station, you have a radio. In order to be able to hit on the frequency, it's not so easy. So even if somebody would try to tell us that something, it might be not so easy to listen to it. And I didn't put it here because it takes quite a while, but if you want to have a look of what happened in this sector, it was in the 70s, the so-called wow signal, which made people to believe that they have discovered something, but it's most probably done to some background events coming from Earth. Well, we are looking in other sectors too. Now, gravitational wave you have seen, but since now we know how to measure neutrino as well, you see here Super Kamiokande in Japan, we might even try to look for neutrinos. Why neutrinos? Because differently from electromagnetic radiation, which get dumped very quickly because it's absorbed, neutrinos are almost never absorbed. So that's one problem for us because we hardly detect them, but it's in the same time an opportunity because they might travel long distances without getting almost any loss. Well, what we know, however, is life is difficult, life is complicated, and it's a matter of fact that from the very first eukaryote cells to the prokaryote cells, the step was huge. Now the living matter, living cells are complicated. They have a structure which is absolutely fantastic and wonderful, and one might wonder how possible is that life gets repeated from zero over and over and over again. That's another very challenging question. We have tried as well to tell to somebody else, look, we are here, look, we are here. And this is a very famous golden-plated kind of encrypted information we have sent with Pioneer 10 and 11 many years ago. You see again Francis Drake here and Carl Sagan, very famous as well, who designed this information. They were thinking, okay, let's assume that in 100,000 years somebody finds it. Let's tell them, first we are intelligent, so we know the transitions of the hydrogen molecules, more or less where are we coming from and things like that. And they were even discussing a bit whether to make them holding hands. Then they decided not, because they decided that if they hold hands, the eventual extra aliens might not understand that these are two different creatures or only one if they are connected. So it was a lot of discussion what exactly to put on board such as the information to be read by intelligent creatures. I choose this one because this is from Avatar, because this tells us that sometimes we are afraid that aliens might come here and kill all of us because they are mean and whatever. But at least this movie drew an attention towards the fact that we are not so very nice either. So we might eventually find ourselves in future some other civilizations, and we might not become the bad guys. So this should be something to be kept in mind also when we deal with this problem. For the Italians who are here, I wrote a book which was dedicated to many of the arguments presented in this school. It was published by Springer. You can find it in the libraries or in the online if you want to have it and to read something more about many of these arguments. So before finishing, I want to show you a movie. Let me see if I succeed to find it. Okay.
What's that?
Oh, nothing.
Sure it's not a 1-minute time machine?
Huh? Damn it. Excuse me. Do you mind if I,
It's a great country. What's that?
Well, it certainly isn't a 1-minute time machine. Damn it. It's my lunchbox.
It's weird. I like weird.
Cool. I'm Lames. I'm James.
James. Are you trying to pick me up?
No. Come on. Do I look that strong?
Are you trying to pick me up?
Yes. I'm trying to.
Try harder.
Hi.
Harder.
Coffee.
Harder.
Dinner. Let me go back to my place
Right now?
and make sweet love.
Oh.
And fuck our brains out.
Finally. I'm so sick of men who can't just ask for what they want.
I want you to spank my bad little boy bottom. Come on, I thought you'd... Yeah, no. I want to spank you.
Oh, we're going right now.
Oh. Hey, you like science?
Science. My 5-year-old niece likes science. I have a doctorate in quantum mechanics.
Oh, you like theoretical quantum mechanics regarding both our perceptions of time and how we deal with universal spatial geography.
Yeah. What's your favorite part?
The butt. We were still talking about science. Time travel.
Me too. Oh, it's amazing. Scary as shit, though, right?
I know. Wait, what? Why?
Well, have you read the chapter on practical application?
Of course, I read the chapter on practical application.
And
I am just gonna hit this little red button here.
excuse me. I'm sorry. Who are you? What are you doing with my book?
Shh. I need to read this real fast. Don't worry. This one doesn't even count. Let's see here. 95 pages? Fuck that. No, I haven't actually read that. Been too busy doing instead of reading.
Doing actual practical time traveling? Have you used that yet?
I don't know. Maybe.
For me?
Does that creep you out?
No, it's actually really beautiful.
You really think so?
Yeah, I've never had a man fight for me before, let alone die for me.
Well, I'm sorry, die? No, I'm still here.
Yeah, not you, exactly, but that's the point of the chapter, right? Time travel's impossible.
It's not impossible. I've done it.
No, every time you've pushed that button, you've created a copy of yourself in a parallel world that exists 1 minute in your past. Your original body dies in the genuine or the earlier universe.
Oh?
How many times?
I don't know. Maybe 16?
Help! Anybody? Oh, nothing.
I've killed myself 16 times.
You know, the bright side is you're the first successful multiple suicide. It's pretty cool. Hey, look. Let's go back to my place and just forget all about this stupid little murder box.
Murder box.
The suicide machine one. Who cares? That wasn't you. It was them.
I can't.
Shit, really?
How am I ever gonna get a boner again, knowing what I know?
Damn it. Regina, too, you better thank me for this. What's your favorite part?
Time travel.
Me too. It's amazing. Scariest.
Scary? What do you mean?
No, nothing. I mean, it's not like this is some multi-dimensional murder box or anything, right?
Huh?
Damn it.
Okay, so that's about the traveling in time and about quantum mechanics and about what could hope about that. So, what time is it? Yes, we have approached the final, let's say, discussions. And before giving you the words of participating to this workshop, I'd like to ask you whether you have some comments or some questions or some... Thank you.